Okay, this is the MA261 Fall 2022 Exam 1. And it looks like the exam was like manually scanned. Oh, I hate them Xerox, but okay. Not my fault. We will work with what we have. Question 1, the curves R1 of t equals t squared 1, and R2 of t equals sine t sine 2t 1 intersect at 0, 0, 1 at an angle theta, where cosine theta equals what? Okay. Well, like two things here. If we kind of just draw out like arbitrary curves, um, and we zoom in like really, really close, uh, if we get the tangent of like this curve right here, it's going to be something like that. I'm going to make it maybe a little bit better, but some vector like that in that direction. But it's going to be much, much, much smaller. Same thing with this one, something like that. So we really want to calculate just the angle between the tangents to these curves that they give us. Um, yeah, and first I think it'll help to find the value of t where they intersect. So I'm just looking at this value and then maybe this curve. So for uh, the first coordinate to equal 0, we just have to have t equals 0. And second coordinate to equal 0, we have to, of course, have t equal to 0. So our t is going to be equal to 0. Okay, and then now let's find those tangent curves or vectors. So we're going to get r1 prime of t is going to be equal to 1, 2t, and 0. And then r2 prime of t is going to be cosine t, uh, 2 cosine 2t, and let me just fix that, and 0. Okay, now let's plug in our t. We're going to get r1 prime at 0 is going to be equal to 1, 0, 0, and then r2 prime at 0 is going to be, we know cosine 0 is 0, or sorry, not 0, what am I saying? Cosine 0 is 1, and then we're going to have 2 times cosine 0, so 2, and then of course 0. Okay, and if we remember the geometric dot product formula, definitely know that for just this class, every exam, we're going to get u dot v is going to be equal to magnitude of u, magnitude of v. Well, what is that? It's kind of weird. Uh, what am I writing? My pen isn't even working. Okay. Times just cosine theta. So logically, if we rearrange, cosine theta is going to be equal to, that looks like cosine 6. Uh, again, whoa, I think my pen is glitching out. U dot v all over magnitude of u times magnitude of v. Okay. And then we could really just let this equal to u and this equal to v. I just think it's a little silly. Let's just do it. Um, let's just use the formula. Shouldn't be too bad. We're going to get cosine theta is going to be equal to uh, dot these vectors. We're just going to get 1 times 1, or 1, all over magnitude of r1 is just 1 times magnitude of r2 prime is going to be 1 squared plus 2 squared, or square root 5. And that is equal to 1 over square root 5. And that is answer, well, I'm 99% sure it's E, but maybe it's scanned incorrectly. Doesn't look like it though. Question 2, identify the surface defined by the equation x squared minus y squared minus 4x plus z squared equals 4. All right, well, this question is kind of tough if you don't know your quadratic surfaces, so hopefully you do. But as a general rule, if we have something like x squared minus y squared plus z squared, um, we're likely looking at a hyperboloid of one sheet because we only have one minus sign. So if we had, say, two minus signs, we're probably looking at a hyperboloid of two sheets. So that's just a quick way of memorizing or remembering that. We're definitely not looking at a hyperbolic paraboloid because that would be something like x equals, or z equals x squared minus y squared, but we have z squared, so that cannot be correct. Um, Ellipsoid, likely not because we have that y squared term. So it is just going to be the hyperboloid. of one sheet because, like I said, we have the minus y squared. Cone, the reason is because um, that's just like something like x squared plus y squared equals z squared. But clearly we have some sort of constant and we have some sort of minus y squared here, which is going to make it so you can't write it in terms of this form. So, okay, answer C is correct. Question 3, a particle has acceleration a of t equals 60j plus 2k, and the initial position is r of 0 equals j, and the initial velocity is v equals I minus j. The distance from the position of the particle at time t equals 1 to the point 223 is what? Okay, so kind of an integration problem here. We have acceleration and we have initial position and initial velocity. We want to find, well, if we find position, like the position function, we can pretty easily find the distance from that point. So let's go ahead and um, I'm just going to write A in terms of like a more vector friendly form. Um, we're going to get 0, 6t, and 2. So if we integrate each term here, we should get velocity. So I'm going to make that more v-like. So v of t is going to be the integral of a of t, which is what we have up there, dt, and that's going to be equal to, we just integrate each of the terms. So we're going to get some sort of constant here. I'm going to leave that out because I'm going to put that later. Um, and then 3t squared. And then again, we're probably going to have a constant, so I'm going to leave a space there. And then 2t. And again, constant. So uh, those constants are important because we basically have the initial velocity. So v of 0 is 1, negative 1, 0. So if we plug in our value of, if we plug in 0 for t, we should get this vector right here from over here. So logically, if we plug in 0, um, I think we're going to have some sort of, we're just going to have 1 here because um, I mean, that's a way to get uh, this vector be 1, and we can't have any t terms because we integrated and we just found it's equal to a constant. So 1 is going to be first component. Second component, if we plug in 0, we're going to get 0. And only way to make that equal to a negative 1 is just subtract 1, because again, we can't have any other t terms as we integrated. Same thing for last component. That actually all works out, so we don't have any constants. So this is going to be our final vector. So basically, we're just plugging in 0 and then adding or subtracting what it takes to get to this value of v. So if we plug in 0 just to check, this term drops, so we get negative 1. This term drops, we get 0, and that is equal to 1, negative 1, 0. Perfect. Now we can do the same thing, integrate velocity, get position. So I guess we're calling it R of t, not R of 0. R of t is going to be the integral of velocity, and that is going to be, we just integrate each of the components here now. So we're going to get t plus a constant. I'm going to leave that out. And then t cubed minus t, and then again a constant, and then just t squared. And I'm just looking, we have r of 0 is going to be equal to 0, 1, 0. That's r of 0. So logically, we're not going to have any constants for our first or third last component, but plug in 0 for here, we're going to get 0, so we're just going to add a 1. So that's our constant. Cool. Just a quick check, we plug in 0, it drops, 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 so we just have 0, 1, and then this last component, 0. So that works out. Always good to check that way. Okay, so now we can just plug in t equals 1. We're going to get r of 1 is going to be equal to 1. 1 cubed minus 1 plus 1 is just 1, and then 1. Wow, that's kind of funny. It's just 1, 1, 1. I don't know. But okay, now let's find the distance. We're going to get distance is going to equal to nice big square root. It's going to be 2 minus 1 squared, or 1. plus 2 minus 1 squared, 1, and then plus 3 minus 1 squared, or 4, and that is square root 6. Wow. Okay. Question 4, determine B so that the line x plus 7 over 4 equals y plus 2 over b plus z minus 1 over 2. Okay. Oh, it's parallel to the plane. 3x minus 2y plus 2z equals 14. All right. So if we remember, a plane is defined by its normal vector and the coefficients in front of that plane, which in this case is 3, -2. That's a negative sign. Maybe not keep it there. And 2 is our normal vector. So we're going to have the normal vector is going to be 3, -2, and 2. So, um, I mean, we have a plane and we have just a normal vector. So that's like 90 degrees right there. Okay. And if we want the line to be parallel to the plane, so if we just like say this is our line, so parallel, um, I'm a pretty bad artist. Wow. Okay. We logically want the normal vector to be perpendicular to that line. So we just have like something like that because the line kind of is in the same direction as the plane. Um, so logically, um, if you don't see it already, these are like the I think it's called symmetric equations. What they did is they kind of set t equals t, where if you kind of derive these equations, we're going to get something like t equals x plus 7 over 4. Um, so we get 4t equals x plus 7, or x equals 4t minus 7. So you can do this for all of the different um, components, but main thing is that like the direction vector in the x direction is just going to be 4, which is just the value right here. So you can kind of apply it to the rest of them. I'm not going to do it because you're going to get the same result. But our direction vector of this line, so which direction it kind of points in, because the starting direction or like the starting value doesn't matter. It's just going to be a shift. It's going to be in the same direction. Is going to be um, 4b2. So this line right here has direction 4b2 as the vector. And since we want that to be perpendicular to our normal vector of our plane, we just dot them and set them equal to 0. So we're going to get 3, -2, 2 dot 4b2 equal to 0. So we have 12 minus 2b plus 4 equals 0. So 16 equals 2b, or b equals 8, and that is answer E. Question 5, let R of t equals 5 sine t, 3 cos t, 4 cos t. Compute kappa at pi over 2, the curvature evaluated at pi over 2. All right, so there are two formulas for this. I prefer the formula where we have kappa of t is equal to um, v of t cross a of t, and over, and it's the magnitude of v of t cubed. So if we remember, v of t is just r prime of t, and then a of t is r double prime, or v prime of t. So we can get v of t, a of t pretty easily. So v of t is going to be the derivative of the components. So we have 5 cos t, -3 sine t, and -4 sine t. Okay, and a of t is going to be the derivative of v of t. Is going to be equal to -5, sorry, sine t now, um, -3 cos t, and -4 cos t. Okay, now I think it's just going to help to plug in pi over 2 because we're working with smaller numbers there. So uh, v of pi over 2 is going to be equal to, if we remember, cosine of pi over 2 is 0. So we can kind of just drop all the terms where we see a cosine. And sine pi over 2 is 1. So we just replace sine of 0, or sine of t with 1 and cosine of t with 0. So we're going to get 0, -3, -4, and then a at pi over 2 is going to be equal to um, -5, 0, and then 0. Okay, so to get these magnitudes, or well, we can actually just, we're going to need to cross them anyways. So let's cross v and a, and that's going to be some sort of determinant of a matrix. So v of t cross a of t is going to be equal to matrix of I, j, and k, I hat, j hat, and k hat, I believe. And let me just make that a little bit nicer to my liking. Okay, it's going to be 0, -3, -4, -5, 0, 0. And it's going to be the determinant of this matrix. So if you remember, the first component is going to be equal to, you like cross out these two, and you're going to get, you're going to multiply that and then subtract, or you're going to multiply items in the diagonal there, subtract by the multiplication or the product of the items in the second diagonal. So -3 times 0 is 0, minus uh, -4 times 0 is 0, which is just a nice 0. And second component, we do the same thing. We're going to get, let me actually keep that. We're going to get 0 times 0 minus -5 times -4, or -20. And let's see here, third and final, sorry, for the middle component, you need to actually just flip the sign. So that should just be a +20. Very important there, actually. Um, I don't think it's going to actually matter, but it's still important to get that right. Um, Last component, 0 times 0 minus -5 times -3, or -15. Okay, cool. So we're done with that. Maybe getting the, what is it? The magnitude of that's going to be a little bit onerous, but we're okay here. Okay. Now we need to get the um, magnitude of that vector. So magnitude of v cross a, I'm just writing v and a now because, I mean, we're pretty good here. Going to be equal to 20 squared, or 400, plus 15 squared, or 225. And I mean, to be honest, I I know what that is, but maybe you don't. So 625, maybe you can estimate it. 20 squared is 400. 30 squared is 900. What's kind of in the middle? Um, Maybe it's not exactly clear, but this is going to be equal to 25. And I think there's a rule there, like a trick that you can use, but um, yeah, I think just I trust you guys that you can get that square root. Uh, okay, so we have that. So that's our numerator, and then we have to divide by magnitude of v cubed. Okay, so let's go ahead and get magnitude of v. It's going to be equal to square root 3 squared plus 4 squared, which is 25. So that is 5. So we have 25, and now finally kappa of 0, or sorry, kappa of pi over 2 can be equal to 25 over 5 cubed, or um, 1 over 5. And that is answer A. Question 6, the level curves of f of xy equals square root 9x squared plus 16y squared plus 16 minus 4y are what? Okay, so if we remember, level curves are, we just set f of xy, or z, equal to some constant and kind of work from there. So let's do that. We're going to get c equals the square root of that nice big thing. Whoa, what happened there? Okay, 9x squared plus 16y squared plus 25 minus 4y. Add 4y to both sides. We're going to get c plus 4y equals square root 9x squared plus 16y squared, and then plus 25. Okay, square both sides. We're going to get kind of hard to draw that parentheses, c plus 4y squared is going to be equal to square root goes away, so 16y squared plus 25. Cool. And then I'm still not really sure what this kind of is, but I think if we expand the left-hand side, we'll get something. So c squared plus 8cy plus 16y squared is going to be equal to 9x squared plus 16y squared plus 25. So just same thing on the right-hand side. And it's always good when things cancel because it makes me feel good and I feel like I'm doing something right. So goes away, goes away. And okay, what are we looking at here? So I am going to do one thing and just kind of regroup constants because constants really don't matter all that much. Um, the only case they really do matter and you need to kind of test multiple constants is where the answers have, they might say like parabolas and sometimes lines, or they'll say circles and sometimes ellipses, but they're not doing that here. So uh, the constants aren't going to matter. So we can kind of just regroup and get 8cy equals 9x squared, and then subtract c squared from both sides. We're going to get just some, I don't know, I'm going to call it k, where k is just k equals 25 minus c squared. And that just makes it a little bit easier to see, in my opinion. So logically, if we divide by both sides by 8c, we're just going to get y equals, again, we could let 8c be some other constant, but really what we're looking at is 9x squared plus k, where that's that constant, over 8c. So if we kind of match this, we're really just looking at a parabola, or answer D. Question 7, let f of xyz equals e to the xy squared plus sine of x squared plus y squared, sorry, x cubed plus y cubed, excuse me, plus ln, whoa, y to the 7th plus tan 9x cubed, compute f of x, y, z equals 0, 3, 7. Oh, I mean, really, looks terrible, right? There is a trick though. Um, Hopefully you see it. We have no z in this whole thing. Therefore, if we try to take the partial of it, we're going to get 0 because it doesn't really matter which order you take these in. We're eventually going to need to take a z partial, and we can't just, I don't know, spawn in a z randomly. So very nice. Answer is 0. And quick trick, whenever you see like really terrible, like I want to say like generally, if you see anything to the power of 4 or higher, there's gonna be like a maybe like not too obvious, but there will be a trick because they're not gonna make you do like ln integral 7. Like that's just not gonna happen. Um, so be wise about that. Okay, question 8. Limit as xy approaches 0, 0 of 1 minus x squared plus 3y squared over 7x squared plus 21y squared equals what? Okay, so immediately when I look at these limit problems, of course, you want to try to plug in 0, the point 0, 0. If we do that, we're just going to get 1 minus cosine 0, which is 1, all over uh, all over 0. So that's 0 over 0, no good. Um, so we need to try something else. I always like looking for things I can factor because that usually helps in a limit problem. So if we factor the denominator, we are going to get, I'm just going to rewrite the numerator, cosine x squared plus 3y squared all over. We can take out a 7, so we're going to get 7 times x squared plus 3y squared. And I'm seeing some sort of like these are lining up. So maybe we can do like a substitution Who knows? So let's see. Let's go ahead and do that substitution. Let's let this thing inside equal to u. So I guess I can just write u equals x squared plus 3y squared. Um, so now, if we transform our kind of limit bounds, we're going to get just limit as u goes to 0 of 1 minus cosine u all over u. And maybe you know this limit from, sorry, 7u. Maybe you know this limit from Calc 2 or Calc 1, I'm not sure which. But if we plug in 0, we're going to get 0 over 0 again. So um, we can use L'Hopital's rule, or again, if you know this limit, you probably know the answer already, but let's use L'Hopital's rule. So we're going to get limit as u goes to 0 of sine u all over 7. So if we plug in that, we're going to get sine 0 over 7. Sine 0 is 0, so our answer is 0. And I guess maybe if it makes it more clear, we can just rewrite this as 1 over 7 times limit as u goes to 0 of 1 minus cosine u all over u. And I'm pretty sure this thing right here, or not that, but this right here is a pretty common limit. So yeah, our answer is going to be E. Question 9, consider the equation x squared plus y squared quantity cubed equals 8x squared y squared. And it's saying the derivative of y prime at the point -1, 1 is what? So whenever we see like some function equals another function, variables on both sides, probably thinking implicit differentiation. And there's like a formula that you can use. If you let, or if you subtract, say like that from both sides and get some sort of big function of f of y, like a big F, x to y is going to be equal to x squared plus y squared cubed minus 8x squared y squared. Um, y prime is just dy dx. So dy dx is going to be equal to the negative of the x partial of f all over f, or the y partial of f. So quick way to remember that, you always take the negative and then you kind of crisscross the x and y's. That's just the way I remember it. There's a pretty simple, or maybe not too simple, but elegant derivation. You can probably find that in the textbook if you want, but yeah. So let's go ahead and find these partials. Um, f partial, or the x partial of f is going to be equal to remember chain rule, so 2x, maybe not actually 6x times x squared plus y squared to the second power, and then minus 16x y squared. Cool. Did I do that right? Hopefully I did. And yeah, so the y partial of f is going to be equal to 6y times x squared plus y squared squared, and then minus, oh, 6, same thing, it's just kind of different. X squared y this time. Okay, so I think it's going to help if we plug in our point. So let's go ahead and do that. So we're going to get x partial of f at -1, 1 is going to be equal to -6 times -1 squared plus 1 squared is 2. So 2 squared, and then minus 16 times -1 times 1. Clean that up a little bit. We're going to get -24. So minus 16, but we have a negative sign, or minus 16 times -1. So plus 16, it's going to be -8. Okay, well, if you made a mistake there, you're kind of done, but I don't think I did. Thank God. Okay, so y partial of f at -1, 1 is going to be equal to, let's see, now we're looking at 6 times 2 squared. We kind of have that symmetry, and then minus 16 times 1 times 1. So we're at same 24, but now it's positive, and minus 16, so we have 8. Nice. So did I do that right? Yep, I did. Okay. So dy dx from our formula above. It's going to be negative fx over fy. So negative fx is -8. So -8 all over 8. And that is just equal to 1. And that is answer B. Question 10, compute the directional derivative d of u of fxy equals xy plus x cubed at the point 1, 2, and in the direction of 1, -1. Okay, so first we kind of need to find that actual, the gradient of f to find the direction that the derivative is kind of, or not that, sorry, to find the direction of steepest ascent, because that is going to be uh, the derivative, quasi-derivative of that function. Um, and then we have to dot it with the unit vector of the direction. Okay, let's go ahead and do that. We're going to get gradient of f x y is going to be equal to, it's going to be a vector of y plus 3x squared. And now it's of y, so we're going to get just x. Great. Okay. So let's plug in our point. We're going to get gradient of f xy is going to be equal to 2 plus 3 times 1 squared, or just 3, and just 1. And that is just 5, 1. Okay. So let's go ahead and now calculate our actual du of f. So du of f, that is a t. Wow. Is going to be equal to that gradient times our direction, but a unit vector. So it's really going to be times that direction u. So that's going to be our u value given in the problem, all over the magnitude of u. Reason it needs to be a kind of a unit vector, and that's really, this is what a unit vector is in this case, is because we don't want to like disturb, or we just want to get the direction. We don't want to change what this vector actually is. Because if we had not made it a unit vector, we'd be either scaling or shrinking that vector, which is not what we want to do. So, okay, let's get du of f is going to be equal to gradient, which is 5, 1, dotted with u, which is 1, -1, all over magnitude of u, which is square root 1 squared plus square root of -1 squared, or square root 2. Okay. That is going to be equal to 5 minus 1 is 4, all over square root 2. And if we multiply by square root 2, multiply by square root 2, we are going to get 2 square root 2. And that is answer C. Very nice. Question 11, consider the surface Z equals 3 minus x squared minus y squared plus 6y. Find the points on the surface at which the tangent plane is horizontal. Okay, so there are multiple ways to do this. If we remember our quadratic surfaces, we're looking at something like z equals 3 minus x squared minus y squared. This y squared term is really just going to shift this conic surface or quadratic surface, and it is a paraboloid because we have like the minus x squared minus y squared. So hopefully you realize that. If you don't, I would just memorize those quadratic surfaces. They're very important. And I guess the 6y, you can think about it in terms of like even just y equals x squared. If we add like a 5x, or maybe that's not a good example, but if we had a 5x, that just shifts that parabola from being from having a vertex at 0, 0 to some, I mean, I don't even know, but I don't remember how to do that. I'm kind of stupid, but okay. Yeah, so we just have a shifted paraboloid, and if we remember, our paraboloid in 3D is going to be facing, like, it's going to be looking downward because we have the minus x squared minus y squared. So if we draw it out, our going to be something like this, but it's not going to be at 0, 0. It's going to be some sort of shift um, because of that 6y term. So if we can find the vertex, naturally, tangent plane at like the vertex should be horizontal, and that's kind of analogous to 2D. If you have a 2D parabola, the point at which the tangent line in this case is horizontal is going to be at that vertex. So really, we're just looking for the vertex of this paraboloid. So we can complete the square, and then we should have our answer. So we're going to get z equals 3 minus x squared, and then we have to kind of factor out the negative sign, which is kind of annoying, but yeah. So let's get minus y squared, and then we want to make this a plus 6y, so we need to do minus 6y, and then we just add a 9 to complete the square. And then since we de facto added uh, a minus 9 to this side, we need to fix that by adding a plus 9. Okay, so everything looks good here, so we're going to get z equals 3 minus x squared minus the quantity y minus 3 squared plus 9. And that is just equal to 12 minus x squared minus y minus 3. That looks a little weird. Squared. Okay, great. So we already kind of have our answer, but we just got to decode this equation. If we think about it, the maximum value of z can be is 12. Reason is because we're just subtracting off positive values. And if we're subtracting a positive value from 12, the maximum z can ever be is 12. So I'm looking at our answers, and A is the only answer that has 12 as the z value, um, which is just our vertex of our paraboloid. And to kind of look at the standard form here, we would have something like z equals 12 minus x minus a squared minus y minus b squared. So naturally, we're going to have x equals 0, and that's right here. And then y equals 3 is right here. So that is all nice. You could also have done this using like the regular tangent plane method, or like finding the max of this paraboloid. But I mean, why would you complicate it when you can do it the easier way? I think this way is just so much easier. But yeah. Question 12, find the relative extrema, I'm not sure, of f of xy equals negative x cubed plus 4xy minus 2y squared plus 1. All right. So let's go ahead. We need to find our gradient of f. So that is going to be it's going to be equal to negative 3x squared plus 4y and negative 4y plus 4x. Okay. So let's see here. Well, one critical point, we instantly have 0, 0, but none of our answers have that, so it does not really help. Um, I don't know, you have to play the game somehow. But if we get second component equals 0, we can get negative 4y plus 4x has to be equal to 0. Divide by 4, we're going to get negative y plus x equals 0, so y is going to be equal to x. Great. So if we use this and plug into our second component, which we also know has to equal 0, um, we can solve and get an actual value. So let's plug in our, I don't know, let's plug in x for y. So we're going to get negative 3x squared plus 4x is going to be equal to 0. This really isn't that nice. I don't like it, but let's divide by negative 3. So x squared minus 4 over 3x equal to 0. Factor this, we're going to get x minus 4 over 3 equals 0. So we have x equals 0, as we kind of got before, and x equals 4 over 3. And that's something that's actually helping here. So let's see. Well, now if we, I mean, we can use this relation up here to just find the value of y. So we're just going to get y equals 4 over 3 as well. Okay, so that's nice. I'm looking at our answers here. Maybe we can eliminate something. We have not found a 2 over 3 value. So looks like A, B, and C, or A, B, and D, sorry, are all wrong. Just because, I mean, we haven't found a 2 over 3 at all. And I don't really know where you could have gotten that. So that is definitely wrong. Now we just need to really determine whether it's a min or max because there's no like indeterminate from our second derivative test option. So we must know it has to be a min or max. Uh, and we can do that with the second derivative, or we can do that with either fxx or fyy. And remember, this component right here is fx, this right here is fy. So we can just take the easier one, really, and I think it's this one because we have less complex squared terms. So I'm going to make that more y. Great. Remember, f, uh, okay, so we have fyy is just going to be -4. So it's going to be a maximum reason because if we think kind of 2D, uh, we could draw something like that. Our slope is getting more and more negative. So our slope is decreasing. So clearly here, our slope is positive, and then it's kind of getting close to 0, and now it's getting down, down, down. So positive, 0, negative, and that is a maximum. So our answer is E.